One of the factors used to identify minerals is their hardness, which means how well they resist being scratched by a harder mineral. So what we're going to do is go through and show you the steps that we would take to show hardness for the minerals. This is talc. This is listed as number 1 on your list. With talc, it's one of the softest minerals, and if you notice that even my fingernail will leave a scratch on it.
Yeah.
This is number 2. It's called selenite. It is also a very soft mineral, and so we can also show that it will scratch with a fingernail. This is called calcite. It's number 3 on your list. This one we can try with a fingernail, but it really is too hard for my fingernail to leave a scratch. So for the next step, we would try a penny, which is made of copper, and we'll find that if we press hard enough, you see it leaves a scratch mark. Fluorite is going to be a little harder than the calcite. This time, the penny is not going to scratch it, but if we take the fluorite, we can scratch the penny. So can you see the scratch?
Yes.
Right there.
Now we see it. Okay.
Okay. So that means that fluorite is harder than the copper. Then we can find something that's harder than the fluorite. If we use a blade, a metal blade, we can actually then scratch the fluorite. So it takes this is going to be harder than the fluorite is because the blade scratches. Okay, we're getting a little bit harder. This is called apatite. This is number 5 on the list. We're going to find that the blade will also scratch it. Now this one's a little bit harder to see. The blade will scratch it.
Yeah, you can see it.
But it's harder. It's harder for me to scratch it with the blade. So that's because this is harder than the fluorite that we scratched before that was a little bit easier to scratch. So we're getting harder each time. This is number 6. It's called feldspar. This time, where we were able to scratch the others with the blade, this one is not going to scratch with the blade. If I press down, even pressing down on it, I can't get it to scratch. So that means this is harder than the blade. But if I take a piece of glass, the feldspar can scratch the glass. The blade is cutting it there. Let me go again.
Yeah, you can see that really well.
Okay, so the feldspar is harder than the piece of glass. This is number 7. It's quartz. And this one is also going to be harder than the glass, but it should scratch the glass a little bit easier because it is harder. Let's see if it does. Very definitely cuts through the glass much easier than the feldspar did. Where we had quartz before, this is number 8. This is topaz. So as the numbers get higher, we're getting harder. So now we're going to take the topaz and see that to prove that it's harder, it will scratch this quartz. But it's a little bit harder to get them to scratch as we get harder and harder. This one doesn't want to leave. Okay, are we seeing anything?
Not really. Yeah, there it is.
Okay, right there. As we get harder, then they are harder. And so we're not going to get as easily a scratch as we did before. Number 8 again was the topaz. Number 9 is called corundum. Corundum is one of the hardest minerals that we have. And we're going to see that it does a pretty good job on scratching the topaz. You see it?
Yeah, get out of focus. Give it a second. There it goes.
Okay, so then the scratch is right there.
Okay.
All right. Once again, 9 was corundum. Number 10, you'll notice that if you see anything if we look at the kit, it's going to say not in the kit for number 10. Number 10 is a diamond. This happens to be in my ring. The diamond is there. We talked about in class that diamonds are the hardest. Diamond, if I could get to the diamond, to the edge of it, it would scratch the corundum because diamond, again, is the hardest mineral that we have. Talk about in your group what can cut or what's going to be able to scratch the diamond. Think about it.
Scale C. In this video, we will show how the Rockwell hardness test works using a gear wheel. The basic idea of this test method is to measure the permanent depth of indentation of a hard indenter under a test force. In the process variant Scale C, a rounded cone made of diamond is used as an indenter. In step 1, the diamond cone is pressed onto the test piece surface with a minor force of 10 kilopons. The depth of indentation under this preliminary load is the reference point. In step 2, the test force is increased by 140 kilopons, which is acting as the major force. This means that an overall force of 150 kilopons is now acting on the indenter, and this force is held for a certain time. In step 3, the major force is removed again. While the minor force is still acting, the permanent increase in depth of indentation E is measured. This is how the Rockwell hardness is calculated. Rockwell hardness HRC is equal to 0.2 minus permanent depth of indentation E in millimeters times 500. Let's take a look at how the test is carried out in practice. The tester selects the conical diamond indenter and installs it in the testing machine. Then he picks up the gear wheel and puts it on the support table. After rotating the microscope lens to its vertical position, he can adjust his test piece. As soon as a focused image can be seen on the screen, the surface of the test piece is in the correct height. The test can start. In modern testing machines, the Rockwell hardness test is fully automated. That's why the Rockwell hardness test is used so often in automated production lines. That's it! The Rockwell hardness of our gear wheel is 55 HRC. This result is displayed on the screen. The hardness of a compressor wheel for a turbocharger is to be measured using the Vickers method. The main principle of this hardness testing method is to press a pyramid-shaped diamond indenter with an exactly defined force onto the test piece and then to evaluate the surface area of the indentation. First, the tester has to prepare his testing machine. He takes the Vickers indenter with the four-sided pyramid and inserts it into the mounting device of the testing machine. He then places the compressor wheel on the support table and rotates the microscope lens into its working position. With a hand wheel, he adjusts the height of the support table until the test piece surface is displayed in focus on the screen. Next, he moves the test piece around on the support table until the right spot for the hardness test is displayed. Now that everything has been prepared, let's begin with the test. After pushing the start button, the diamond pyramid pans down and carefully touches the test piece surface. The test force slowly increases to its specified value. After holding the test force constant for a certain time, the indenter lifts again, pans back, and the microscope lens resumes its former position. This is the magnified indentation on the display screen. With a control knob, the tester now places 4 measuring lines at the corners of the indentation. Doing that, he can easily measure the length of the 2 diagonals. Finally, he only has to push the input key. The Vickers hardness value will then be calculated automatically. It is equal to the test force F in the old unit kilopond divided by the area of the indentation A in square millimeters. The Vickers hardness of our compressor wheel is displayed on the bottom left-hand corner of the screen and amounts to 125.